All right. The OSI reference model is a kind of generic reference model in order to kind of break up the different functionalities needed into kind of handleable layers. So let's discuss what is needed and how to handle it. Okay, so this is the kind of generic OSI reference model. So let me give you an example of what is really needed to, for example, transmit emails. Say, for example, I wish to transmit an email to my grandmother in Bangalore. Okay, how do I do that? Well, first of all, I have a laptop, and the laptop has an application running on it which generates this email, which is a bunch of bits. These bits have to go from here, College Station, to Bangalore, which is in India. How will they get there? So let's work our way up the different requirements. So first of all, I've got bits, right? These bits, say my laptop is connected to a wireless access point, right? It's somewhere in the roof here, perhaps down the corridor. And so what you need to do is convert these bits into electromagnetic waves, which can be received by the other end. That is called the physical layer. So the physical layer is the medium through which transmissions happen. Now I cannot just transmit and hope for the best. I need some kind of modulation, because wireless operates in the Wi-Fi operates in the low gigahertz range. So I need something which will modulate the waves so that it gets to the other end. Okay, so far so good. Do my waves get to the other end is the question. The answer is not necessarily, because somebody might be running a microwave, there might be a generator running. There is a lot of electromagnetic noise which corrupts the system. So anything that I transmit, there is no guarantee that it will be successfully received at the receiver. So in other words, is that me? No. Okay, so what we need is a means of reliably getting my bits across to the access point in the roof. That is what the data link layer does. It does coding primarily to ensure that these bits which I transmit do indeed get across. Okay, so in particular, we discussed this in the last class. The simplest, or shall we say most stupid coding scheme would be just transmit everything 3 times, right? I want to transmit a 1, I send 3 ones. I want to transmit a 0, I send 3 zeros. Now you notice that will immediately make my rate of transmission 1/3 of the useful stuff, which is very inefficient. There are more efficient ways of doing it. But that is to ensure reliability of the link between myself and the access point. Now the data link layer needs to do one more thing. It's not just me who is transmitting in College Station at this location. There's a whole bunch of other guys connected as well. So just because I transmit a packet, there is no guarantee that nobody else will be also transmitting, and so there could be collisions. And what will collisions do? Cause interference at the receiver, and the packet is lost. So in other words, you need to also ensure that the medium access is controlled. By medium, I mean the free space between here and the access point. And by access, I mean only one of us hopefully should transmit at a time, so that the receiver gets the packet successfully. And so the data link layer does these 2 jobs. It ensures kind of reliable transmissions and does medium access control to make sure that only one person transmitted at a time. It's not exactly accurate to say only one transmits at a time. There are various methods of doing medium access control, which we will learn later on. But loosely speaking, it is accurate to say that it's to ensure only one guy transmits. Okay, so far so good. So where are my packets now? They are in the access point on the roof. My grandmother, of course, is not sitting there. She's in Bangalore. So it needs to go across the world to get there. That's why I need a network, right? So a network is composed of lots and lots of these links, each one with its own physical medium. Some of them might be wired links, some might be wireless, some might be optical fiber, etc. All those have to be joined together, and I need to find a route from here to Bangalore. Now, if I was to fly an airplane, for example, which I can't, but if I were to, I would need to use GPS or some method of knowing where I am to get to the other end. If I were to send mail, for example, it uses a zip code in order to be transmitted from one location to the other, to the other, to the other, and eventually wind up at the other end. So in the case of the internet, you use something called an IP address, an internet protocol address. So essentially what this network layer does is it routes across the world, the network, in order to get to the other end, right? We will learn about routing algorithms and so on to ensure shortest path routing to get there. Okay, now I have a way of getting across the world. Now the problem is that there are lots of people sharing some of the links which I'm using, and some of my packets might be lost not due to electromagnetic interference, but due to excessive congestion on some of the links, or because of buffer overflows. So in other words, the rate at which I transmit in an end-to-end fashion is not determined by this one hop to get to the access point, because I need to get to the one hop and the next hop and the next hop and the next hop. So I need end-to-end a method of essentially choosing my rate. I should make sure there is no congestion, and of course I need to make sure, as we discussed last time, that I do not overwhelm the receiver. My grandmother's laptop or Android phone or whatever is quite different from what I'm using here. So on an end-to-end basis, I need to ensure that I do not overwhelm the receiver, which is flow control. I need end-to-end reliability, packet losses must be handled, and I need congestion control to make sure I don't overwhelm any of the network links. That is handled by the transport layer. Now, the session presentation layers in the current internet have been subsumed into the application layer essentially. Well, some of the session layer ideas are in the transport, and the rest went into the application. So loosely speaking, you can argue that these layers are all in my web browser, right? So when she clicks on her Gmail or whatever, it will take care of all of these. The purpose of these is to pull those bits which are coming off from the transport layer and do something with them. In this case, represent it as an email. Okay, so that is essentially the reference model. This OSI, Open Systems Interconnection Reference Model, was not actually implemented. It took so long for people to standardize it that people came up with the TCP/IP stack, which essentially became the de facto model. But it's still worthwhile to look at it as a model describing what needs to be done. Okay. Now, there's a little bit more to this. So what's going on here is the following. So this is my station, station 1, and this is my receiver. Let's call them station 4. Right. The point is, in this example, there's 2 hops to get there. You have to go to location 1, 3 hops totally to get there. And so I have a router here and a router there. Right. Actually, let's call 2 and 3. Right. So that is 1, 2, 3, 4. Okay. So the question is, do these routers have to do all this stuff? They really aren't interested in the content of the email. Who cares what's in there? So clearly, they don't have anything to do with the application presentation, whatnot. These routers are also not interested in end-to-end reliability or anything. That's my business. It's my business not to overwhelm my grandmother's computer. So that has to be done on my end of the thing. Similarly, end-to-end reliability, my grandmother, if her computer determines that packets have been lost, it's its job to tell me. It's not the job of the in-between routers. So they have no business doing transport layer. But what they do need to do is have all the lower layers, because the network layer, if you remember, interconnects all these media together. So it needs to know where to go. In other words, the network layer on this router R2 is basically needs to forward to R3, which then forwards to the eventual destination S4. So in other words, we need the network layer to operate on all the in-between nodes, and certainly we need the physical and data link layers, because there are physical media through which my packet has to traverse, and those physical media have to be reliable, otherwise the packet won't get there, and the network layer will ensure that it gets to where it needs to get. As in, if for example this router has 3 different places it could go, it needs to determine that it has to go to R3 and not to R5, R6 or R7. So it needs to know where to send it, and then this guy similarly determines where to send it, and life is good. So essentially in this reference model, therefore, all the layers are required at the 2 end hosts, while only until the network layer are actually used in the in-between hops. Okay, so let's look at this in a little more detail. So here is the physical layer. We'll spend a reasonable amount of time on each of these layers. We'll spend less time on physical, because primarily this is communication, and if you take a course on digital communication and electromagnetics, you essentially will learn this stuff very well. You've already taken a course on electromagnetics at some point, I guess. Digital communications, some of you probably have taken. But we won't focus too much on this, because really we want to go higher than this layer. But I will spend some time discussing this. So what is the physical layer? It is the actual physical medium, all this mechanical stuff, cable, plugs, pins, all that stuff. And of course, there is a modulation scheme which ensures that you can transmit signals across this. And there's various different things which you use: Ethernet, DSL, cable modem, telephone modems, etc. Each of these has a particular medium that they are kind of supposed to operate over. And the mediums in question could be twisted pair cables, coax cables, etc. I will discuss something about modulation on these schemes, on these media. And I will also discuss a little bit about what is the capacity of these media. Something about Shannon information and that kind of thing, just a little bit. But the point is, this is the physical medium over which electromagnetic transmissions happen. Okay? So that's our first layer. The next layer, as I said, has this requirement to ensure that my transmissions are successful over that one hop. Also, medium access control, that not too many people talk on it simultaneously. So here we are. So what this data link layer is going to create entities called frames. These frames are essentially the unit, you can think of them as packets, but as they apply to the data link layer. So they're units of data, and essentially they will have some way of detecting errors in this data, and I will describe coding schemes for doing so probably next week. And you also need a medium access control method to ensure not too many people talk simultaneously. Once you've got your data link layer in place, you have a means of transmitting frames over single hops successfully, right? And now you have to connect all those single hops together to form the network layer. So the purpose of this is to transfer these packets. So you start calling these units packets now across multiple links and or multiple networks. So it goes from one end of the world to the other. So these nodes will jointly execute, as I said, a routing algorithm. We will learn a bunch of routing algorithms to get you from your source to destination successfully. And of course, they have to forward these packets across each node in order to get to the other end. Then there is the transport layer. So the transport layer's job is this end-to-end scheme wherein you reliably, with flow control and congestion control, you get from one end to the other. As part of this, you have to set up your connection, maintain it, and release. TCP is what we'll use for this. And then there's the other layers, application, session, presentation. Essentially, all of this stuff is in the application layer. And that's finally your web browser or Skype or whatever you're using, which pulls these packets off your socket and does something with them. And the something with them is what you are finally interested in. Okay? Now, each time a packet goes from one layer to the other, essentially it adds on its own header. So your application, Skype or whatever, creates the data. It might have an application header saying this belongs to Skype. When it goes to the transport layer will add its own header saying this is TCP, this is the packet number, etc. When the network layer, you'll put on an IP header and say this is where it has to go, etc. A data link layer, it will put on essentially a CRC check and a data link header. Essentially together, these form the full coded packet, which essentially the data link layer can tell if the packet was successfully received with no bits in error or whether it could correct them, etc. And the physical layer takes these bits, modulates them, and sends them off. Okay.